My name is Cosmin. I'm a software engineer at Keysight in the Romania office. I've been doing networking, computer networking, not social networking, for 14, 15 years now. I started my career at Ixia. In the meantime, Ixia was acquired by Keysight, and here I am. Today we're going to talk about CPU hyperthreading because it was an important part of how we can configure computers for highest throughput network traffic. So we stumbled across these issues, and I wanted to learn more about hyperthreading, and then I said to Florian, I want to prepare a presentation, and here I am. So let's start. Let's look at the agenda. So we're going to talk about the so-called execution units of a CPU. Then we're going to learn what is hyperthreading and how hyperthreading was first launched with Intel Pentium 4. And then we're going to see how Linux supports this, and DPDK, which is a networking thing, supports this. Okay, so the execution units of a CPU. In this picture, it's nice, lovely colored picture. What this picture is a build-off view of a CPU. That is actually no. So there are two kinds of peel-offs. One is actual physical peeling off the die, the physical die of a CPU. But this one, I think it's so colorful because the Intel or AMD engineers wanted to do a nice Photoshop view, right? So here we can see how the transistors of the CPU are organized, and we can somehow see that they are grouped in I don't know how to call them. In the end, they are grouped into some units. So here, for example, we have the first core, the second core, the third core, the fourth core. Here we have the associated cache, memory controller. All are grouped in specific, let's call them regions. But in the end, they are all formed of individual units. So for example, let's consider this chunk here. It might be a specific execution unit. So the main idea here is that a CPU is comprised of different units. So let's have a look at this picture here. You probably are familiar with the CPU-Z, the tool which shows nice information about the CPU. Here is a sixth generation Intel i7, so it might be from 2013, who knows? 2016, thank you. Okay, so what we want to look here is this instruction set, because it shows what features the CPU supports. For example, EAS, which stands for Asymmetric Encryption.
Advanced Encryption Standard.
Thank you, Florin. Advanced Encryption Standard. Or AVX, which stands for Advanced Vectorized Extensions. Thank you. Okay. Now, if we put this in a separate rectangle, we can note the MMX unit, SSD unit. It does not matter what the unit does. It's we only want to see that the CPU has these units and they are available, and we can see what units are supported in the CPU. Okay, so different units are used for different applications. For example, video streaming might use the SSE unit more intensively as compared to the some financial applications. We might use the encryption and the security functionality of the AES unit, or in gaming it might be using the MMX unit. It depends. Okay, now a little bit of computer introduction and how computers can run our programs. Well, it might be that the most important units in a CPU might be the so-called control unit, CU, and the register unit. The control unit is used by our program to make decisions. For example, it might take the first branch or the else branch. As I mentioned here, it might be used for branching and jumps, whereas the register unit is simply the group of registers which are used by the program. AX register, BX, or for example on ARM registers we have from R1 to R16. So it's the register unit. Now let's look at a program, and here I made this curvy arrow here, which might mean is the thread, the executing thread of a program, in comparison to a thread which means used in sewing. So a program thread is simply the execution flow of a program. So the main characteristic of a program is that it cannot, it has like an epic thread used in literature. You read page by page. You don't want to jump at the middle of the book and then start from the beginning, because it will not make any sense. So here a program thread is similar. It executes the instructions in order. It might have some branching, some jumps, and some other instructions. Let's look at what execution units a CPU can use at a specific moment of time. So the main idea here is that a program cannot use multiple units in the same time. So here, for example, if we have the first instruction is a branch, is a if condition, it will use the control unit. Next, if we have an addition, the program will be executed by the CPU and it will use
arithmetic logical unit.
Arithmetic from the arithmetic logical unit. Thank you. Next, it will do a division. It will actually use the floating point unit. Thank you, Florian. Good. So here we can see that at a specific moment of time, a single unit of the CPU was used. What is hyperthreading? Well, what the Intel engineers realized in the late 90s, I think, early 2000s, was that most of the time a single unit of the CPU is being used and the rest of the units remain idle and probably consume power, and the CPU gets hotter and hotter. So what the Intel engineers did, they simply duplicated the control unit and the register unit, and in this moment we can run two programs, right? Because the simple fact that we have a control unit and a register unit is enough to run a program. So let us have a look. Here we have two programs and they can simultaneously be executed. Let's have a look. So the first let's call them program A, or the first program executes this if instruction. We have these blinking lights over here. It says that the control unit, the first control unit in the CPU is being used by program A, and then the second control unit in the CPU can be used by program B. So basically we execute this in parallel. Next, when the first program does an addition, we see here the blinking, it might be in yellow or orange here. The ALU unit executes the add instruction for the first program, whereas the second program has a division and it can use the floating point unit in the CPU. So at this point we already use two units, which is a big improvement compared to the previous non-hyperthreading processors, which had to serialize the access. Next, the first program does the division, and the first program will be using the floating point unit, whereas the second program does an addition and uses the ALU unit. Now let's see what happens if we run the same program. So both programs start, they use the control unit, but then they both want to use the ALU. So now it depends. Most likely the first program it will have access to the ALU, and then the second program will have to wait. So at this point we have a stall in the pipeline of the second program, because it has to wait for the first program to execute the instruction, and only then the first program can continue. Now we can see that the first program advances and it can use the floating point unit, whereas only now the second program can use the ALU unit. Okay, and in the end, the second program will finish. So we could see that the second program was delayed, and this might impact the performance, as we'll see later. Now, let's have a quick overview of what is the processor, what is the core, and what is a logical core. So, as stated on the Intel web page, if you buy a processor, you can find information, or actually before you buy a processor, you can find information about the specifications of a processor. Here we have an 11th generation Intel i7. It says it has 8 cores, and because hyperthreading is enabled, it has a total of 16 threads. Now let's see how this will show in a. So I spent a half an hour doing this PowerPoint slide because I had to copy paste a lot of units. So we have a single processor. So you go out and buy. You'll be receiving a single processor in the packaging that you buy from Intel. So you have a single CPU die, physical die, but inside Intel cloned 8 cores, and inside each core Intel cloned the control unit and the register unit, and we have a total of 16 threads. So this is basically what Intel provides, and they call these logical cores, these 16 threads. Okay. Now, if we go back in the days when Intel first released this Intel Pentium 4, so the Pentium 4 was actually started in 1998 and should have been called Intel Pentium 3. But because Intel started a new architecture, it was called the net burst architecture, so the engineers could not make the processor in time, and instead Intel was pressured by AMD probably, and Intel launched Intel Pentium 3, which was similar to Intel Pentium 2. It was using the same architecture, but it had a higher CPU frequency, probably more cache. So Intel Pentium 4 was actually, as I mentioned, had to be launched after Intel Pentium 2, but because of some delays, it was launched after Pentium 3. So the first release of the Intel Pentium 4 was in late 2000, but the first Intel Pentium 4 with hyperthreading enabled was launched after 2 years. So, of course, it was not an easy thing to do this hyperthreading thing. A lot of I don't know, issues with manufacturing probably, or testing, so who knows, it got delayed. Now, if we look at the same colorful, yes, please.
What's the difference between hyper-threading and multi-threading?
We'll get that in a few slides. Okay, now let's look at this Intel Pentium 4 Northwood, which should be the first, no, we also have a Northwood here. So, this Pentium 4 Northwood here has hyperthreading enabled. And let's have a look at what the Intel engineers actually had to duplicate in order to make it hyperthreading. And I highlighted these blinking parts, blinking text here. So if we have a look, the register alias history table, it does not matter what it is. We only can see that it's somehow symmetrical. We have some units above and some units below. Let's also look at this return stack. Where is the arrow? So I don't know what's there, but there are two rectangles. Let's look at this one. This one is more visible. It says front-end branch prediction table. So we can see that they look like two alkaline batteries, but it's the branch prediction table. We can see that Intel had to double these units. If we look here at the bottom, it says level 2 cache. Okay, so we also, Intel had to double the Intel 2 cache. But if we have a generic overall view, we can see that the number of doubled units is, I guess, less than 5%. But the performance improvement might be more than 40% in improvement. So it was quite a revolutionary idea to only double a few units, but be able to run in parallel the other rest of the units. Oh, here we also have some double units. Okay. So the main question was, why did not Intel duplicate the multiplied by 3, I don't know how to call it. Triple, thank you. Triple the logical cores. So instead of having 2 logical cores, why don't we have 3 logical cores? Or 4 logical cores? The answer is, if we do have a speed up of 30-40% with 2 logical cores, most likely the triple version had a speed up improvement of, I don't know, less than 30%. But probably in some cases it had lower, even lower speed up improvements, and it was probably hard for them to market, or the haters in the industry would say, okay, I have three logical cores, but the performance is 5%. Why are you selling this to me? So I actually had the pleasure, I think it was in 2012, I had the pleasure in the lab, we had a Spark CPU. It was the last generation of IBM, it was Sunblade? I don't know, I can't remember right now. So it was a server with Spark CPU, and it had 4 logical cores. And as you can probably realize, Spark is long way dead. We have not heard from back then. So most likely their idea with 4 logical threads did not scale, especially in the server industry. Okay, Now, let's have a look on how Linux has support for hyperthreading. I made this test on my HP workstation. It's a Z4 Generation 4 server. It has a Xeon server, so this Xeon naming is a bit confusing. Even from the late 90s, Intel branded their Xeon processors as Xeon, and they still do in the present. It's not like we can figure out from the branding if it's a newer or older CPU, but this one I think is from, I don't know, 2020. It's a server CPU, as I mentioned. It has 4 cores, and with hyperthreading enabled, it has 8 threads. As previously, 1 CPU, 4 cores, and then 8 logical cores. But if we do this cat proc CPU info on my Linux machine, we see that Linux is not particularly specific if a processor is being in a hyperthread, that is, if it's a specific logical core or a different processor. So for example, Linux is generic about this. We might have, so it says we have processor 0 on core 0, we can see this from the core ID. We see processor 1 being on core ID 1, so it's most likely here. And if you scroll at the end, we see processor 6 being on core ID 3, so they have the flexibility of not even correctly incrementing the core IDs. We have core ID 0, core ID 1, it jumps to core ID 3, and core ID 4, the last one. And if you can see at the last processor, it says Linux, it says processor 7, we see core ID 4, and it's actually the last logical core from here. So Linux treats the logical cores as processors, and we can see that this, yes, please.
It's actually a reason behind the numbering on the cores. It's not actually correct. Usually use numbers 0, 1, 2, 3 for the first course, and the hyperthreaded one. This is why you see the core ID. The core 0, for example, will have 0, 4. The other one will have 1, 5. The 3 will be 2, 6, and so on. This is why you see it. And this is basically the same for mostly all architecture that you see that are named. So this is why you're seeing this. It's not Linux treating this, you know.
So you don't mean about core 0, core 1, core 3, right? You don't mean about this. This is how Intel
What I'm trying to say, like seeing it in form.
Yes.
Why you're seeing on core 6 the core ID 3?
Yes.
It's because actually you're skipping one number like that, but it's the logical cores.
Yes.
You're having that for core 0 will be 0 and 4.
Yes. So, one second. So, if we look here, I did a Linux has this support. It has this sysfs file. It's called sys devices system CPU 0 topology, and then siblings. Siblings means like brothers. We can see indeed, like you say, CPU processor 0 has the sibling processor 4. So we have here 0 and 4. This is what you mean?
Yeah.
Okay. And then processor 1 has the sibling of 5. We can see here. And then if we go at listing the CPU 5, we see that CPU 5's sibling is 1. So they are both siblings. Okay, so okay, thank you. Now, if you wonder how Linux can detect these somehow hard-coded in the processor settings or information, it's because the Intel CPU offers this CPU ID instruction on Intel architecture, or that is on Intel CPUs, and it's quite a big datasheet that you need to learn if you want to do this by hand, but if no, Linux already has support for parsing this information in the CPU. So these ones are hard-coded at manufacturing time by the Intel manufacturing engineers. And using this information, we can actually find information, for example, the physical ID. Here we have a single CPU die, as I mentioned, with different CPU cores and so on. Okay. Now, let's talk about software threads, about the difference between software threads and hardware threads. And at this point, I hope to answer your question, what's the difference between multi-threading and hyper-threading, right? Okay? So a software thread is more what the programmer or developer or user might think about the thread. So it's being a software thread is more close to the software engineer, the one who compiles, loads, and what not does with his processor. So we have a process. The process might be multi-threading, that is, it has multiple threads. These are software threads. Whereas when we talk about hardware threads, the hardware threads are more close to the Intel engineers, the one who design the CPUs and are able to run multiple threads on the same CPU. So let's look at this example. So we have a CPU, we have one core, and then with hyperthreading enabled, that is 2 logical cores. A hardware thread can run 2 different processes. So the hardware thread does not necessarily have to run 2 software threads. So let's say we have a process, single-threaded process, and then let's take an example. Let's say you have Firefox, and then you look at some YouTube streaming on your computer. This process might be single-threaded. It might be executed by a hardware thread of the processor, and then you might have another process. I don't know. Some examples. What else do we do? PowerPoint, or me recording this presentation on the other process, on the other hardware thread. So it's a different process. For the CPU, it does not make any difference if it's the same process or 2 processes. So the idea with hardware threads is that it's more close to the processor and not to the software. So a processor can run 2 tasks in the same time, two processes. Hyperthreading should have, in my opinion, hyperthreading should have been called hypertasking, because it can run multiple tasks and not necessarily the same threads of a single program, of a single task. Okay, so the difference between multi-threading and hyper-threading is that multi-threading means that executing 2 or more threads in the same time in one processor, compared to hyper-threading, which only means that it can run 2 hardware threads on the same core, hyper-threading. Okay, thank you. Let's look at some benchmarking. This was not done by me. Some engineers did a matrix multiplication. So if we go back to university and or actually back in the high school, and we want to multiply 2, what's the plural for matrix? It's matrices, thank you. If we want to multiply 2 matrices, we get the first row from here, we multiply it with the first column and so on, we have a result. So it's a nice pseudo algorithm in here. We don't go into details. What we can notice is that if we have a program, so this is a not so good example of when to use hyperthreading, because when the CPU does most of the time the same instruction, so it means we run the same execution units of the CPU, the speed up is not that good. So with hyperthreading enabled, we might be, let's say, 10% faster in some cases when we need to multiply a matrix of size 1000. Whereas, if we look at the efficiency, and this it might be some metrics for the managers or the IT department who said, okay, I'm going to buy a hyperthreading processor for you, and you'll have double of the efficiency. Whereas we can see that this is not true. Hyperthreading on the efficiency is quite half because we have the efficiency is the speed up divided by the number of processors. So our program runs in parallel, but the efficiency is half. Yes.
Is this actual data that is measured?
No, this was done by other geeks. I did not do these measurements. But it's from the same web page, so I suspect that it's from the same algorithm.
What I'm trying to understand is why this. I mean, this graph is not.
It's mostly using the ALU.
No. It's the actual data. It's 20% efficiency. This means you're using 5 times more resources for the same speed up. If you're enabling hyperthreading, I don't think you should go unless your code is behaving way worse, which is the case in general with hyperthreading enabled for the computational intensive code. It shouldn't go under 50% of the, for example, the second time, the hyperthreading one, should be half of the first one, at most.
And it's higher than half, you say, right? So here we have 0.9, and you say that it should not go beyond 0.45 here?
For each data point.
For each data point. Oh, okay. I'm not good at math. I don't know. I hate graphs and reports. I simply don't. I'm sorry. I don't understand either why this efficiency.
It expects by doubling the number of hardware threads, the maximum theoretical efficiency to be twice, and it compares with that. It divides by the maximum theoretical efficiency. Well, speed up, the maximum theoretical speed up, which is 2x, and the efficiency will be lower.
So what I can tell you for sure is that I did read this paper. So without hyperthreading, we have a single CPU, right? And this program runs with no parallelization, right? So we have a single program. Whereas with hyperthreading, somehow they do parallelize. This is correct.
Yes, but the expectations are higher, are double, and that's why the efficiency is
lower.
Is half, because the expectations will not be met.
What I'm trying to say is that based on what we have observed on maximum computation, if you have hyperthreading enabled and you parallelize with the maximum number of logical cores, usually it is worse than having hyperthreading disabled and parallelizing half of the logical cores.
This slide, right? You say that no. With hyperthreading, we have better speed up.
In the real world scenario, no. I can guarantee that on a matrix multiplication that is big enough, not doing 0.1 seconds matrix multiplication. In Blast or whatever, if you do this, you will see that it's worse.
I think that the code was inefficient because it should have iterated. The matrix should have been organized in linear. Well, the second matrix should have been transposed
It's a
beforehand.
huge, yeah, it's a huge discussion. It's row major
Yeah,
versus column major.
exactly that.
For example, here the OME4, it's not collapsing and you have a lot of jumps.
Both,
Usually when you do
both
this, it
hardware
doesn't
threads
collapse.
will wait on the memory to fetch each line,
So the K and J should be.
which is shared.
Exactly.
And those are cache.
The memory access is not, for example, for in this scenario, when you're doing A of I and K,
Mhm.
uh,
Both threads will wait for the memo to bring the data into cache.
no, the BKG, it's a non-sequential access to the memory. BKG. You iterate with most inner loop, K. You iterate and you jump from J to J, which means you jump from N to N, which is the size of the. This is why I asked you if it's something that you should try to fix.
I actually had wanted to know are there any differences in how layer 1 cache is organized when hyperthread is enabled?
Yes, they both share the same layer 1 cache, and it might
And that's
affect the other
non-sequential
cache threads.
Yep.
Okay, let's talk afterwards. Okay, DPDK is a networking thing. More recently, they added DPDK to block devices, but that is to hard drives and to storage. DPDK stands for Data Plane Development Kit. It's a project started in 2010 by Intel. They made what Intel did. They were able to create a framework to generate network packets with high throughput, and then they made this open source. I was, what, are you crazy? And then I realized that actually Intel might better sell their network equipment by doing this, so doing open source. So it's a nice thing. Thank you, Intel, for what you did. DPDK, as I mentioned, it's a framework that it's some code written in C++, which is able to generate network packets. That is some buffers you can think of, and then send them to the network card. What we have here is we have a computer with Xeon. I think it's an old Xeon here. We have a core with hyperthreading enabled. What this DPDK layer 3 forwarder means, it's a program which simply reads the packets from the network card. So we have a 10 gigabits per second network card here with 2 ports. It reads the packets from the first port, and I think the arrow here should be in the other direction, that is, it forwards. It receives the packets on one port and it forwards the packet on the second port. And here at the bottom, of course, we have a Ixia traffic generator, because Ixia can generate up to 800 and more gigabits per second. So this is not this is a slide from the internet, honestly. So this is what some so I did not create this slide. It's from internet. We can see what we can see here is that so DPDK runs and keeps this CPU at high CPU load usage. And then on the other logical core of the same core, uses this stress NG. NG stands for new generation. Please don't name your programs NG, because in 10 years they'll be deprecated, and then what? You'll call them NNG2. What these slides are showing us is that if we don't start stress NG, we have the normal DPDK thread doing its business at full utilization, but as soon as we start stress NG on the second logical core, it means that it will start using some of the execution units of that core, and we can see that the performance of the first core drops. So DPDK will not be able to generate line rate, as we call it, that is 10 Gbps throughput. It will start to go to 0.9, and in the worst case, socket workload means that when we talk about socket, we mean about the connection between the data bus between the CPU and the memory. So if we start a StressNG application which makes a lot of memory calls, this is the one which drops the performance badly. We'll have a nice live demo about this. We have a machine over there with two fiber optic network cards. We'll see what happens when we start StressNG. Why disabling hyperthreading? Because some gamers discovered that their Florin's a heavy gamer here. Some gamers discovered that their games run better with hyperthreading disabled, either in real-time OS, because we don't want one of our cores, which should be doing.
Just a really quick.
Yes.
You go again. Most older games are not ready.
Most older games.
Most older games. Yeah. Most of the newer games are trying to make use of the hyperthreading.
Okay, so old games you mean. Okay, most old games are using single threaded. Okay. Thank you. I'm not a gamer. I mean, I do play some casual games. Thank you. Well, in real-time OS, what means is that you want to have an application which respects the deadlines. You don't want your application to be slow or have non-deterministic behavior. That is, if we do have a CPU which most of the time delivers the deadlines, I mean, you expect some tasks to be executed in, let's say, one millisecond. If you do have some naughty other thread which runs on your other logical core, it might create problems for your real-time program. So this is why you might want to disable real-time hyperthreading. Hyperthreading can be disabled in the BIOS. You can see here hyperthreading, or it might appear under the name multiprocessing, or AMD calls them symmetrical multi-threading. So you can disable this from the BIOS as well.
And the best reason why you should disable multi-threading is security, because multi-threading on the newest CPUs was discovered to be a very, very good side channel vector.
Thank you for it. This is a slide. So please, after I show this slide, you know more about me. So the thing here is that when you have a processor with hyperthreading enabled, your legit program, let's say you want to do some banking or I don't know what, something using security like encryption and so, your program can run on the first logical core. It might use the AES unit, as we could see in the beginning of the slides, the cryptographic unit of the CPU. It might do encryption or decryption or whatever. And then I don't know how to call this, let's say a hacker, malicious process, thank you Florin, might execute in the same time with the other core, yes, and then it might do some timing measurements, because it can find out, so let's say the first processor uses the AES unit, the second malicious process waits because it also wants to use the AES unit. It has to wait for the legit program to complete, and then it can make timing measurements, and then it can use this to figure out what algorithms, encryption algorithm you use, or who knows. I don't know these things.
The encryption key.
The encryption key. Thank you, Florin. So as I said, while one logical core is using the AES unit, the other logical core can make time measurements. So in conclusion, hyperthreading is a nice thing with about 5% CPU die increase. We can get up to 40% performance increase because it reduces the idle time of the other units in the processor, and it might also reduce power consumption. One note here is that ARM processors are very good at shutting down specific units if they are not used. So ARM processors are quite good at this. So yeah, good overall performance. If you have questions, if not, we can show the demo and then you can have the questions. Let's show a demo, right? Okay, so here we have DPDK. No, not here. Here. No, not here. Here. So let me start this DPDK application. As you can see, we have this fiber channel cable here. It's important not to twist it that much because it will break and the connection will drop. It's not like Ethernet cables, which are more rough. Now, let's start DPDK. I'm going to type here start 0. What this means is that the first port, I don't know, it started blinking, but I don't know which is which. We can see that it sends 14 million packets per second. So at the lowest frame size, which is the Ethernet standard says that you need to have at least 64 byte frames on Ethernet network cards. So at the lowest frame, we have 14 million packets per second. This one port on the third column here, the second port. Let me start also the transmission. Start one. At this point, we can see that the second port transmits 13 million packets per second, but it's only receiving 10,000 packets per second. 10,000 million packets per second. I don't know why this. It doesn't matter. What we can see here is the CPU utilization. We can see that DPDK uses 3 CPUs at 100%. I can tell you that on CPU 2, it's the packet processing, the program which creates the packets and sends them and also receives them. Now, as an experiment, we're going to start the stress tool on CPU 10 because CPU 10 is the sibling of CPU 2. That is the hyperthreading on that core is between processor 2 and processor 10. So let me open up. Let me open up a new window here. We're going to run this tool. It's called StressNG, and then it does a T-search. So it's not like bubble sort or it's an algorithm. I'm not good at algorithms. It runs something stressful. We simply use this command. It's called task set at the beginning of the command to force the StressNG tool to run on CPU 10. It says here 9, but this is because it starts from counting from 0. So let us start the stress tool. If we can look here, we can see that CPU 10 started doing CPU intensive operations, and if we look at the throughput, we see 10 million packets by port 1, 10 million packets by port 2. So we already have lossy performance. We had some customers complaining why their performance dropped from time to time, and this is the reason we had hyperthreading messing up the performance. If we go back and stop the stress tool, we can see that the performance jumped to 30 million packets per second. So indeed, that slide over there, which some other engineers did, is correct. I was actually a bit upset at the beginning of me trying to do this demo, that is a month ago, because I was only generating packets from the first port. So let me show you. If we do stop 1, which it will stop transmission on the second port. Now we can see that it goes up to 14 million packets per second. We can start the stress NG tool, but it will do the coping just fine. It will not have any issues. Actually, no, it goes to 14 to 13. I can't remember. I know that I tried a lot of like bubble sort and other algorithms in StressNG, and I was not able to degrade the performance of DPDK, but now it works fine. Okay, any questions? Well then, thank you. Hope to see you next time.